This is QMG, the quantum mechanics guy. Today I have something very exciting to talk about, and it's more on teleportation. As you can see right here, experimental realization of control quantum teleportation of arbitrary qubit states via cluster states. Sounds sophisticated, but they have nice graphic information in this article, so it makes it very easy to follow. Also, this article gives you blueprints so that you can go practice in your quantum computer. You can try the IBM platform. I recommend it. It's a lot of fun. Now, what is teleportation? Well, teleportation is the appearance of one state in somewhere else without transporting the state there, right? So you must be able to establish coincidence between two events in order to be able to teleport information. If you're doubtful about teleportation, what it can do, examples of teleportation, watch my video on teleportation so that you can see a live example using the platform for a quantum computer. So you can actually see my numbers and see how teleportation actually works, right? So in this paper, they're going to talk about a specific kind of teleportation. And I would like to mention that this paper was recently published, and I'm surprised it hasn't gotten too much attention. So I will go over it because I think it's a very interesting paper. Okay, so this one talks about a specific form of teleporting. Usually when the teleportation that I did, for example, if you watch my video, it's a teleportation between two systems with a medium system. Okay, so the way in which wow, look at that. Usually the way in which teleportation occurs is you use an agent in between in order to entangle two systems, and then you entangle the other two systems, and that allows you to teleport this one into the other one. So the one in the middle allows you to teleport. And of course, there are many schemes that allow you to do that. I presented in one of my videos, one that involves 3 parts, but of course, they can be very complicated. So I'm going to show one that is like that. Okay, so let me just read the heading, okay, because I think they do a very good job in presenting the case. Control quantum teleportation involves a third party as a controller for the teleportation of states. Here we present the novel protocols for controlling teleportation of the arbitrary 2 qubit and 3 qubit states through 5 qubit and 7 qubit cluster states, respectively. So you can see right away they're going to be using more than just one medium state to teleport information from one state to another. In this scheme, Alice sends the arbitrary qubit states to the remote receiver Bob through the cluster states as quantum channels under the control of Charlie. Bob can recover the mentioned states by making appropriate unitary transformations, and we point out that the efficiency in our scheme is 100%. Okay? In the process of our analysis, we find the classical communication cost in our protocol is remarkably reduced when compared to the previous protocols. We performed the experimental realization of the above protocols on the IBM 16 Melbourne, yes, I've been using that one too, quantum computer and the IBM quantum simulator, and we calculate the fidelity. We also examine the security analysis against Charlie and the schemes which we consider here are secure against Charlie's attacks. Okay, so 2 things that this improves, right? The cost. Okay, in other words, it's more efficient to do it this way. And in the other teleportation schemes, you have to establish once you establish a certain base between Alice, the one sending the message, and the medium state, that information has to be sent to Bob in order to break the information. So in teleportation, you need a key. in order to be able to unlock the message. So technically speaking, teleportation can be done instantaneously, but the downside to that is that you might get the message, but you don't know what to do with it unless you have a key. So um, this scheme is technically more efficient when it comes to doing that. Okay, so that's what they are trying to imply with the efficiency, the cost, and let's look at the what they did. And the best way to do it is to show you a picture, right? So here it is. Okay, wow, the teleportation scheme that they created. As you can see, if you look at A on the top, they have the information goes on A and B. All right, let me take my brush here. My brush right there. Okay, cool. All right, so information goes right there. And right here, these ones are used to teleport the information, right? That's the medium. As you can see, they have 5, and they mention a 7 one. Okay, 7 gates, and you can see, and the reason I like to show these ones to inspire people to actually do them, because they can be, you can take this information and you can actually do it in your quantum computer. You can use the same computer they use, the 16-bit one. I recommend it. I've been using it. It takes a little bit of time to get results. Okay, but it's worth it. Okay, so as you can see, they create right here. They use something to entangle the system, and they enter the information there, and it should come up on the other side. And notice here they have the firm measurement. So right here, this part, that's where you modify the information that comes in at some point in order to, so you take the information that comes out of measurements. I hope, hopefully I can slide it. Probably that's it. Maybe it shows some more information. You can enter the information right there, and this medium allows you to teleport somewhere around down there. I don't think I can see the measurements. Let me try to see if I can erase and move this one upwards. So yeah. Okay, so let's see. Let's look at Alice performs the necessary unitary operations on arbitrary 2-qubit and 5-qubit cluster states. Okay, let's not give more than that. Okay, theoretical experimental realization. So they actually did this experiment. They run it. Okay, this is what I wanted to see right here. I suppose they did the measurements somewhere. I was looking for the measurement gates. I suppose they did it somewhere around here on the right side. All right, so that's the 5-qubit one, and then they have a longer version, the bigger version of that. That's the 7-qubit one, and as you can see, look at this. For this one, you can actually enter 3 qubits. Okay, so allows you to pass more information in one burst, which is very good. But you need more qubits in order to do that. And here is what you do after you get your measurements, I suppose. Alice performs the necessary unitary operations, an arbitrary 3-qubit, 7-qubit cluster. Now, one reason I like this paper, it gives you right here, gives you a nice summary what's going on teleportation. Okay, you gotta keep these ones in mind if you ever want to come up with your own teleportation scheme, so that you don't reinvent the wheel. Okay, if you've been following my channel, there's my brush right there. Okay, good. All right, so if you have been following my channel, I have used some of these ones here, like that one. I have been using that state right there. As you can see it. Let's make it bigger. Let's make it bigger. There you go. So those states should look familiar. So with those states, you can actually create a nice teleportation scheme. Okay. There's my brush. I keep looking for it. There it is. Right there. That one should be very familiar to you, and you should know how to make those like that in a quantum computer, right? and they call it the GHZ state. That's not the GHC state. I don't know what they're talking about, but oh, I see they use it as a channel. Okay, so you can, so this one's right here. I don't know why they call it a GHC state. That's not it, but I guess you use that one as a channel to do that one. And right here at the bottom, you're looking at the one that they have. The protocol. You see the contrast. So I see the channel right here is the 5 qubit cluster state and the 7 cluster state. And what you enter in the previous ones are those right there. Okay, so I see the advantage right here. As you can see, this one allows you to enter more in one shot. Okay, right here, notice. It allows you to send more in one shot because the other ones right here are sort of restricted to something that looks like that, right? And sometimes you want to send more than that, right? Something more complicated than that, okay? So you might want to try this one in your quantum computer at some point. And here's they actually, well, this one is a repeat. I don't know why they put it again, but this is a snapshot of the mediating state, right? So that's the one that is allowing in between to do the teleportation of information. Quantum circuit generating the 5 qubit cluster. Okay, cool. And of course, there's the description of that state. Okay, so if you wanna test yourselves, try to make that one without looking at the circuit. Let's see if you can make it. And as you can see, they obtain their results eventually. Let's see. A generalized circuit for teleporting arbitrary 2 qubit states using 5 qubit clusters. So there's the one. Oh, here it is. I knew that happened. So here's the measurements that they do. As you can see, you have to take some of the information from qubits 2 and 5, okay, in order to, you have to take some information. You have to adjust some of the qubits on this side, as you can see. And let's see, they do some computations right here. Okay, so it's very clear, I think, what they do. And of course, I'm not going to go over that one. So all of these can be done in very nicely in your quantum computer, your platform. And there's a 7-1. So this, notice, oh, look at the 7-1. I like the 7-1. Look, a generalized, wait a second, a quantum circuit generating 7 qubit cluster. Oh, look at how beautiful this one is, how symmetrical it is. You can see, oh wow, you can see the advantage of the 7. Oh wow, look at this one. How simple it is to use 7. Wow, very symmetrical, as you can see, to generate that type of, to use that one as teleportation medium. Okay, and of course they got their results at some point. And the reason I bring this paper, okay, there are the results. Okay, so yeah, they compare the two devices, the simulator and I guess the other device. I see. It says here, histogram comparison between the probabilities obtained by the IBM CASM simulator and the IBM 16 Melbourne for teleportation of 2 qubit state. I see. So this is a way of comparing, how good it is actually at teleporting. And of course, these results look better than the ones that I obtained. Okay, so it's a very, I guess, in that sense, if you look at okay, so something very practical. If you look at the way I teleported, I question all the noise that I got, all the errors that I got. So I guess my scheme is not as efficient. And this one, you can see more clearly the results. So there is a huge advantage. That's something that I have learned from programming the quantum computer, is that you really have to think how you're going to do your program, and not everything works really well. This one works apparently very well based on the graphs that I see. And let's see, they got, okay, here we go, more results. So these don't, okay, so, all right, so yeah, the results, I guess, yeah, okay, so that's more like the results that I obtained. That was good, I guess, as I expected. Yeah, well, some of them are good. Okay. And there's the comparison between one device and the other. Okay, and this is, yep. I see histogram comparison between the probability to obtain the IBM CASM simulator at the IBM 60 million for teleportation of 3 qubit state. All right, cool. Okay, and again, this one looks, if you look at my teleportation thing, this one looks pretty good. Okay, I wonder if did they get rid of all the noise? Okay, did they account for the noise? Okay, so that's a very good question. The fact that they just compare two devices, maybe it's a way of obtaining something significant just by comparing the two devices. Well, that's a thinker right there. Okay, and let's see what else we got. Okay, so yeah, so let's see, experimental density matrix, imaginary part versus the real part. Okay, and of course that's what you would have expected. All right, so the point of this paper, okay, you can come up with your own teleportation schemes, and as you can see, they're doable. You have a tool in front of that is accessible to everyone, the IBM Quant platform. I think there are more out there that are coming up. So you can do your own experiments. You can publish your own papers. As you can see, play around with it, because you might be the next one publishing a paper. I can tell you, I'm working on my own papers that I can publish, that I can test. I'm working on, well, I shouldn't say it in this video, but it's a very interesting one, okay? So keep looking at this information, because this might be the next thing, okay, for you. All right, this is QMG, the Quantum Mechanics guy. See you next time.